6.3 is multiplication and division of rational numbers. Fractions is what we're talking about, of course. One thing to sort of be aware of is that it's actually easier to multiply and divide fractions than it is to add and subtract them. The reason that's the case is because addition and subtraction requires denominators match in order to be able to work with the problem. So we have to do, often have to find common denominators. And multiplication and division doesn't require that. In particular, multiplication and division, if you have A over B and C over D, is defined simply as the multiplication of the numerators over the multiplication of the denominators. Now, we don't always do it that way. Sometimes we simplify things before we actually get to just the straight multiplication. But you could do it that way all the time, and it would work. So I'd like to give you a visual description, a picture of why this actually ends up working. Why should it be multiplication across the top, multiplication across the bottom, and that actually yield the right answer? So the example we're going to take a look at is a rectangular region. And we're going to multiply the fractions 3/4 and 3/5. Okay? I said it backwards, but. So what I want you to do is I want you to draw a rectangle. And we're going to do it in columns. Okay, so we're going to make 5 columns. So pretend like this is a cake. And the first thing you do when you cut up the cake is you split it into 5 columns. That is actually what my daughter did last night when she made scotcheroos. I don't know if you've ever had them before, but if you ever have an opportunity, like Rice Krispie treats with butterscotch chips in them and peanut butter and chocolate chips and it's all melted on top. It's amazing. Yeah, maybe I should make them for you sometime. All right, 3/5 is the number that we're actually trying to represent. So we're going to shade in 3 of the 5 columns. Okay, so we'll just kind of create a word picture as we're going. We have this pan of cake, scotcheroos, whatever. And, before it ever makes it to church last night, we can pretend that 2/5 of it disappeared because people in my house ate it. That would be so sad. People at church would be sad. All right, so what we're going to do then is we're going to cut the pan of cake or whatever in the opposite direction into 4s. And we're cutting it into 4s because the denominator on the other one is 4. Okay, that's why we're using these numbers. 4 is a really nice way to divide because you can divide in halves and halves agains. Okay, so we still have 3/5 of the diagram shaded in. But 3/5 of the diagram is actually how much showed up at the church last night in my pretend world. And then what's going to happen is we're going to eat or not eat or whatever. We're going to shade in our diagram 3 of the 4 rows. So this is row 1. This is row 2. And this is row 3. Okay? So this is 3/4 of the 3/5 I took to church. Count for me. How many boxes are sort of double shaded at this point? 9. How many total boxes did we end up making when we cut our pan apart? Total boxes, the entire thing. Shaded, not shaded. 20. There are 20 little boxes in there. Yeah. It might be hard to count from a distance, I'm not sure. But there are 20. It's a 5 by 4. So there's 9/20ths of the diagram that's currently shaded in. And if you take a look up here, of course, that is what you have when you multiply across the top and across the bottom. Okay? So it's sort of like you're partitioning something in 2 different directions, if it helps you to think about it that way. A few theorems and properties are what's going to come next for us. Theorem 610 is the identity and inverse properties. The multiplicative identity says that 1 is the unique value such that when you multiply 1 times A over B or A over B times 1, you get back A over B. That is nothing new. We have that for whole numbers. We had it for integers. It showed up, for those of you who've done number theory with me before, it shows up a long time earlier in this particular textbook. But it's still true. A multiplicative inverse, this is the first time this shows up, though, in this particular description, because we don't always have them, because we aren't working with number systems that have multiplicative inverses. So a multiplicative inverse is a number that you would multiply a over b by to get back to 1. So in particular, if you're talking about the number a over b, then b over a is a unique number such that when you multiply a over b times b over a, you get 1. We also have another name for this. I think it's probably in here later, but in case it's not, it's reciprocal, right? A multiplicative inverse is another name for a reciprocal. Multiplicative inverse, although longer, is a little bit more descriptive than the word reciprocal about what it's doing for us or where it comes from. All right, a couple more properties. Theorem 611 talks about the distribution of multiplication over addition. And it works just like it does with whole numbers as well. If we have a over b, c over d, and e over f, rational numbers, and we are trying to distribute the a over b across those parentheses, then we end up getting a over b times c over d plus a over b times e over f. And then we would proceed to multiply like we talked about at the very beginning of this lesson. Straight across top, straight across the bottom, if you wish it. Okay. So we have a multiplication property of equality, and then in a moment we're going to have one of inequality. It says we have two equal fractions and we multiply both of them by an equal number. It won't change the statement of equality. So a over b equals c over d. Then if we take a over b times e over f and c over d times e over f, then we actually have the same answer on both sides. And we use this, of course, in solving equations. Right? How do we get rid of the 2/3 x, the 2/3 part of it? Well, we multiply by 3/2. We multiply by the reciprocal on both sides. So we use this when we're solving equations pretty heavily. The other one we actually see used a lot when we're solving inequalities. We just don't solve inequalities quite as frequently. Again, those same fractions, a over b, c over d, e over f. But the difference is we're taking a look at what happens when we multiply by a positive number compared to a negative number. So if the direction of the inequality is that we have a greater than, I don't know that I want to make that look like an equal sign, I'm going to shade it, a greater than symbol, and we multiply by a positive number, then we still have the greater than symbol. Okay, so we multiply by positive values, the direction of our inequality stays the same. But anytime we start multiplying by negatives, it flips around inequalities. So now again, it starts out greater than, but I multiply by a negative. And when I multiply by a negative, the direction of my inequality, in this case the greater than inequality is where it started, becomes a less than inequality. Okay, it only happens for multiplication and division, which is the inverse of multiplication, but we'll get to that one in a little bit. Chapter 6 is the most heavily languagey chapter like this. So all of our other chapters won't have near as many theorems just embedded in them at the beginning. So thank you for bearing with me through that. Let's move on to an example. Are you guys good? Yeah? Okay, so I mentioned these are used heavily. Oh, I'm sorry, one more. It was sneaking there on the bottom. It's so small. Multiply by 0 and you get 0. That's all it says. It's a very exciting one. All right, now we're going to do an example, as promised. So I mentioned these are used heavily in solving equations, and this is kind of the question that I was referencing when I mentioned this idea. So in order to get rid of the 3/4 that's currently being multiplied by the x, one way to think about it is, well, the way I get rid of multiplication is I divide. And that's true, you can, but it's usually not real pretty to look at 1/5 divided by 3/4. Right? Fraction division embedded like that just kind of reeks of mess. And so it's easier to work with those multiplicative inverses that we just talked about. And instead of dividing by 3/4, we multiply by the multiplicative inverse, which would be 4/3. And as we do this, we're going to identify what it is property-wise that we're using. And then sometimes we're using more than one property. So here we actually are. This is the multiplicative inverse property, right? That's why we chose the 4/3. But what allowed us to actually multiply on both sides and not change the values on the sides is the multiplication property of equality. Okay, so we chose the 4/3 because of the inverses, multiplicative inverses, but they're actually going to stay the same by doing that on both sides because of the property of equality. Now, the reality is that when I multiply these together, what is 4/3 times 3/4, ignoring the x part? 12 over 12, which is 1. Yeah. So we get the number 1. So this is 1x. Okay? I know you don't usually write down the 1. Well, we're going to make it go away in a minute, but I want to show you that there's actually a property going on there that you sort of take for granted every time, too. And then over here, I'm going to multiply across the top 4. Across the bottom 15, so we have 4 over 15. So as I did that, when I multiplied the 4/3 times the 3/4, what ended up happening is that that's the multiplicative identity, right? When you multiply something by its multiplicative inverse, you get back the multiplicative identity. And then we actually end up, of course, recognizing that 1 times x is just x over 4/15. And that's, again, the multiplicative identity coming out in that particular part. If you want to reference sort of how you can make this one, this is just the definition of multiplication. You could write that down. Not a bad idea. Any questions on that one? So we're about to do a harder one. Well, it's asking in the directions on this particular one to identify the properties used. So you're doing your best to justify what's happening and why you're allowed to do it. So we're not going to be like super picky. Like if you leave like one little detail off, that's not my point. But the point is to kind of start recognizing that these properties are used all the time and we just take them for granted. All right, let's take a look at another one. This one's more complicated. It has more pieces. I have 2x over 3 plus 1 over 4 equals x over 6 minus 1 over 2. There are actually a lot of ways you can start this problem, some that have kind of very little to do with the properties that we've been discussing. I'll try to stick with the properties we've been discussing just because that's where your book is kind of having us sort of sit for the moment here. If our goal is to solve for x, we need all the x's to be sort of on the same side, right? So the first thing that we would want to do in order to accomplish that would be to move the x over 6 from the right to the left. So we will put minus x over 6 on the right and the left. And we'd also want to move the 1/4 that's on the left to the right, so we would subtract the 1/4. Now I'm not going to actually do any subtraction. I'm just going to rewrite this for the moment so that it looks cleaner. So 2x over 3 minus x over 6 equals negative 1/2. Don't forget that negative, minus 1/4. So what kind of properties did I use? There's actually 3 properties I used. What kind of properties do you think might have taken place as we did that? It was nothing from multiplication, right? Because we didn't do any multiplying. I'll get started with one of them. One of the properties that took place here was the additive. Good grief. Property of equality. That property said you're allowed to add something to both sides. You're allowed to subtract something from both sides and it doesn't change anything. So just like that multiplicative identity of equality that we have now, or multiplicative property of equality, we have an additive property of equality that we did last section. Any other ideas? why did we choose, let's just focus on the 1/4 for a moment. Why did we choose to put a negative 1/4 on both sides? Why didn't we do negative 1/3 on both sides, or negative 4/7 on both sides, or what was it that made us choose this specific number right here?
So that we could get the original equation, all the x's on one side and all the y.
Yeah, in particular, we looked at this, whether we thought about it this way or not, and we said in order to get rid of this, I need something that makes it add to 0, right? These two things add to 0, agreed? They don't really disappear. I mean, they do, and they don't really exactly even move. They're disappearing or moving, that sort of idea, because they're adding to 0, yeah? So what you're actually seeing happen there is that we also have two more additive properties. We have the additive inverse property, right? That's why we chose the number we chose. And we have the additive identity property, right? So that it became 0, specifically 0. Okay, so let's actually follow our multiplication. And there's more than one way to do this, I said so. But we'll follow the definition of multiplication from the very beginning because I haven't actually done that yet, which is to simply multiply things across when we have that opportunity. And to do the same thing with the addition where we multiply sort of across and multiply with a smile, remember, underneath? Y'all remember that from last time? So if I do that, then I'm going to multiply like this in order to get the fractions to merge together. So I'm going to get 2x times 6, that's 12x. 3 times negative x, that's negative 3x over 18. And on the right side, we'll just put the negatives with the 1s on top. So negative 1 times 4 would be negative 4. 2 times negative 1 would be negative 2 over 8. All right, so it's 12x minus 3x. 9x over 18. I'm going to go back and get the properties written here in just a second for those two. Sorry, got a little bit ahead of myself. And how about negative 4 minus 2? Yeah, negative 6 over 8. Okay, so what's going on here? Well, the first one right here that I accomplished just a moment ago, sort of step number 2, was this was the theorem of addition of fractions from 6-2. And all that's happening here in step 3 is just simplification, right? We're combining like terms. Okay, but hopefully when you saw 9 over 18 and 6 over 8, you thought to yourself, they're bigger than I need to be, the numbers individually. I can reduce those fractions. So what could I divide the 9x over 18, each of those pieces, by to simplify? I can divide them both by 9. So that would actually become x over 2. How about on the right-hand side? Yeah, I can divide them both also by the same a value, 2, and I can get negative 3/4. And what's allowing me to do that is actually the fundamental law of fractions. All right. Many things we could do right now. I have a feeling I know what you're going to tell me, but what would you like to do right now? That's a good one. I actually think that's the best choice. Most of the time, students will tell me cross and multiply because they see fractions on both sides. And that's okay. You could do that. But I like what Emma said. This is our simplification at its sort of bare bones. If I simply multiply by 2, I would end up actually getting the x alone. So this would give me x equals negative 6 over 4. as we multiply by 2 like that, do you know what property we're actually using? It's a multiplicative property, right? Because we multiplied. Why did we multiply by 2? Just basic description. Why did we choose to multiply by 2? Somebody say because we divided by 2. Somebody say it. Because we divided by 2. That's exactly right. It was divided by 2, so we're going to multiply by 2. So the reason we're multiplying by 2 really is because when we divide by 2, it's the same as multiplying by 1/2. 1/2 or multiplication or 2 in the denominator are equivalent. So this is the multiplication inverse and the multiplication multiplicative identity at play. That's why we chose what we chose. And then, of course, we're going to reduce that, right? So what can I divide both of them by? Yep, 2. So my x actually will here equal -3/4. And again, we've already seen that property already in our description here, but this is the fundamental law of fractions. In shorthand now. Did I write something down wrong? Oh, I did. 3/2. Thank you. 3/2. It's the fundamental law of fractions. Any questions on that one? There's a lot going on behind the scenes, kind of, that allows you to do what you've been doing for so long when you solve these kinds of equations. All right, we're going to start a little bit into division. Well, I think we're going to get the division done. We'll stop at exponents today. So taking a look at division of rational numbers. If a over b and c over d are rational numbers, and you want to take a over b and divide it by c over d, and it yields something like e over f, that will work if and only if e over f is the unique rational number, such that a over b equals c over d times e over f. So I know some of you are probably thinking, well, we just flip, right? We change to multiplication and we flip. That's a process that we're going to take a look at here in a second. That's not actually what this is talking about. This is talking about how is it that this actually works. And if you have seen this before and earlier in this textbook, perhaps with me, this talks about the idea that the reason that 5 is a terrible number, let's use 6. The reason that 6 divided by 2, I'm using whole numbers because they're easy for us to work with in our head. The reason that 6 divided by 2 is equal to 3 is because 2 times 3 equals 6. That's the reason it's the answer, right? So oftentimes when you're teaching division early on, or even sometimes not early on, you'll be asking yourself, or you might be asking somebody else if you're working with them, what times 2 is equal to 6, right? If they're thinking in terms of multiplication better than in terms of division. And that's all this is actually talking about, is that if we moved the value to the other side and multiplied, we would actually get the same as the original value we started with. So what is the actual process or algorithm for dividing that I referenced a moment ago? Well, the idea is that if we have a over b and c over d, and we divide a over b by c over d, that's equivalent to multiplying a over b by d over c. And so we flip the second fraction. Important, it is always the second fraction. My 5th, now 6th graders this summer, they were flipping everything. That wasn't working for them this summer. Kept having to tell them, we only flipped the second fraction, right? Really is only the second fraction. I'd like to talk about why, and this is probably where we'll end today, because it looks a little bit like magic. We'll just flip it and multiply. I mean, why would that work? I mean, it's great that it does because we already know how to multiply, so great, but why would that work? Well, the reason it works is this. If we have a over b divided by c over d, that's a c, just didn't look like it. Another way to write that in that sort of horrible fashion I mentioned a moment ago being not so nice, is a double fraction. All right, that's what division means. It means I can write it with a fraction bar between the values. It just ends up meaning I compound my fractions like this. It's actually called a complex fraction when you see fractions inside of fractions. So how do we get rid of this fractions inside of fractions bit? Again, there's more than one way to do it, but the way that makes the most sense for justifying what's happening here is that, well, the reason that I have the c over d here in the denominator, or the way I can get rid of it, I should say, is by multiplying it by its reciprocal, right? Its multiplicative inverse. Well, that would be d over c. But of course, if I multiply the big fraction in this by d over c on the bottom, I have to multiply the big fraction's numerator by d over c as well. So why did I multiply this? Well, the reason I did is because c over d times d over c is equal to what? 1. So this ends up becoming a over b times d over c divided by 1, which is simply a over b times d over c, which is what we said it was supposed to become up here. So it has to do with this idea of shifting things around and making them look nicer in different ways. So we will pick up on example number 4 next time. But for this time, I'm going to go ahead and have you, or allow you to shift and to get into groups and take a look at the examples that you have, not examples, but the practice problems or the group work problems, however they're labeled in your notes from section 6.2.